And good afternoon to everyone. I'm Israel Garcia. I'm coming from the University of Seville in Spain, and I'm going to present a work that we are actually developing for decades in the University of Seville in order to improve the failure criteria for composites. So in particular, I will be presenting today a problem that it's the objective is to introduce the effect of residual thermal stresses on the transverse cracking of cross-ply laminates. I'm going to explain a little bit the motivation in the next slides. Okay, so typically in the industry, we use a lot the multidirectional laminates, and in particular, one type of the most simple one type of multidirectional laminates are cross-ply laminate. That is what I'm showing here in the slide. That I think everyone here know, but I'm going to remember that. Cross-ply laminates that are composed by 3 layers that where we have 2 external layers with the fibers oriented along one direction that normally in the experiment is the direction, the loading direction, and we have another internal layer where the fibers are oriented perpendicular to this direction. And in this laminate, in this kind of laminate, we have some problem of cracking that we name transverse cracking, and they are cracks that are perpendicular to the load direction and are located inside the internal layer where the fibers are perpendicular to the loading. Actually, this is very academic problem, this cross-ply laminate, that actually they are more or less representative of what happens in multidirectional laminate. That is what is used actually in the industry. So we are going to focus on this cross-ply laminate to study this phenomenon of transverse cracking, but actually the results are more or less can be more or less extrapolated to other multidirectional laminates more complex. So in this problem of transverse cracking, the composite community has worked for a lot of time actually, but I would like to highlight the most surprising result. And it is the result that was made in the 70s of the last century, so they are quite old, but they are still a matter of the subject of a lot of research that we are doing in our group, but also in other groups all over the world. So this result, the experimental result by García, they are very simple, actually experiment that what they did are to modify the thickness of the internal layer. So they tested different laminates with different thicknesses of the internal layer, and they tried to record when the first crack in this layer appeared, at what level or the strength they appear. And they found something that was surprising at this age, and is surprising actually today, and this is that the strain level for which this first crack appeared depends strongly on the thickness of the internal layer. And this is surprising because you can't predict that with the typical failure criteria that we use for composite, like Hatchin criterion or Saihu, or etc., because normally the strain level is more or less associated to the stress that we are going to find inside this layer, this internal layer. So more or less, we don't expect that the strain level for which the first crack is going to appear depends on the strain. But the experiment by these researchers and others that confirmed that after found that. But in addition, you can't explain that with the linear elastic fracture mechanics, assuming that we have some micro crack inside the internal layer. So at this stage, even nowadays, the typical criteria that we use to predict failure in composites are not able to predict this size effect that they found. So when we have some experiment that, let's say, contradict the typical theory that we use to predict failure, typically in science, there are many people that propose another theories in order to explain and predict this phenomena. And in particular, there are a lot. You can imagine the experiments are quite old, and there are, along this decade, there are a lot of criteria that have been proposed to explain this size effect. And also, this is very important for the fracture community because some of these criteria have been extrapolated to other materials and other totally different problems. Here in this scheme, we are just highlighting the four main criteria that are used in the composite community, and in particular the Borchak criterion of theory that is the most popular. He received another names like the in situ strength, etc. But all of them, the one that I highlighted here, can be categorized in two types of models. Ones that are based on a stress model and others that are based on an energetic model. And we have also other, that is the couple criterion, that combine the two. That is very important for the next thing that we are going to do. So this theory is trying to explain and predict more or less well this phenomena, this ice effect that can be predicted by the classical theory to predict failure in composites. But they don't take into account the residual thermal stresses that we can find in this kind of laminates. If you go back to these slides, you can imagine that if we fabricated that in an autoclave in a high temperature, and we have a different coefficient of thermal expansion in the different direction of the lamina, when we decrease the temperature from the curing temperature to the service temperature or the test temperature, we are going to have that the compatibility between the different layers are going to be prescribed, and in this case, the stretch and the contrast between the different layers are going to be different, and that's gonna generate some kind of residual thermal stresses inside the layers. But we know that, but if we do some calculation with the laminar theory, we can get that for modern composite, the composite, for example, used now in the aeronautic industry, these residual thermal stresses in some cases can reach 50% of the transverse strength of the lamina. So it's very important, but they are not taken into account in all the previous model. Only in the incremental energy criterion is taken into account in the proposal by Hachin, not the Hachin criterion, another proposal, but they are very important. So the objective of this work is to introduce the effect of these residual thermal stresses on the analysis of this problem, on this theory, on these different theories. Why they don't, as up to now, they are not in these theories? The reason, I guess, is that the first experiment that they, for example, García and other co-workers did, they did in glass epoxy, where the contrast between the directional properties of the coefficient of thermal expansion is much lower than in carbon epoxy. And in addition, the fabrication procedure wasn't the typical autoclave curing and so on. So they don't expect it. They don't expect actually great residual thermal stresses. So this outline of how we are going to try to do that. First of all, we are going to, well, we have finished the motivation, and now we are going to see how to modify these models, trying to explain the size effect. And after, we are going to go for a experimental validation that actually they are preliminary, actually experimental campaign that we did recently. So we are going to focus now on the different theories that explain the size effect. And in particular, we're going to start with the models that are based in some manner in a stress analysis. So now the laminate is in vertical. So we have in the external layers with the fibers oriented vertically here, and the internal layer with the fiber oriented through the screen. And we can obtain the stresses, assuming linearity. We can obtain the stresses by two partial problems, one that is more or less mechanical. This just applying the mechanical strain monotonically, and another one that is more or less a thermal problem where we apply just the increment that will be decrement actually of temperature. And with the addition, again, assuming linearity, we can compare that with the transverse strength of the material. Of the lamina, sorry. So we can use the laminar theory for that and some dimensional analysis. I think you all know this kind of analysis. So, and with that, we can obtain some analytical formula, an analytical expression, sorry, for the stresses of the partial mechanical problem and for the partial thermal problem. And that is actually in our papers are written entirely. We have here this expression, this function that depend on the material and the laminate parameters. And with that, any kind of stress analysis that assume linearity, etc., like the Weibull, for example, analysis with the stresses can be expressed in this manner with the Weibull adding the statistical part, of course. And if we rearrange all of this, we obtain this where you can observe the mechanical strain. Okay, that is the mechanical strain that you are imposing with the machine. And here we have a term that comes from this term from the laminate theory. And this term, we can assume that is some kind of equivalent strength due to the residual thermal stresses. So with that analysis, what we obtain is that the effect of the residual thermal stresses is just to add a term that can be calculated analytically to the mechanical strain that we are measuring in our machine or we are applying in our structure. This is for the theories based on stress analysis. What happens with the theories based on an energetic analysis? We can try to do the same superposition. We assume the same, actually the same partial problem, but just with a crack that we assume that is symmetric and is in pure mode 1, is perpendicular to the law of direction. And with that, we can assume this superposition for the stress intensity factor. And as is in pure mode 1, we can go to this superposition for the energy release rates. And this energy release rate will be what we will be using for the energetic analysis, either directly, like in the Borchardt problem, for example, in the Borchardt theory, or integrated for the, for example, the finite fracture mechanics. But in general, if we are able to get G, the energy release rate, we will be able to apply any of these criteria. Well, we have G, we need G, actually, the energy release rate for each partial problem. And we did that with boundary element. We can do that with finite element also. But if we do with boundary element, that is what we did, and normalize the result for G with the stresses that we obtain for each problem for the corresponding problem in the stress analysis that we did before. I mean, with these stresses here, what we obtain is that actually the G is the same for the thermal and the mechanical problem. And this is very interesting, but because it avoids us to calculate a thermal problem. Actually, we obtained that numerically, but it was proved by Professor Mantic some months ago. Well, with that, we can calculate the value of G for with the same strategy actually than before. So the G is given by some parameters, but with respect to the load, it's given by the addition of the mechanical strain that we are applying, and this term that again is the same than before, but is the equivalent strain, let's say, that comes from the residual thermal stresses. With that, we can apply directly any kind of energetic approach that are based on G in some manner. But that is the case of the previous theories. So what happens with the model that combine the stress and energy models? For example, the coupled criterion. Since we have that the residual thermal stresses, the effect of them are the same for the stress models and the energetic model, for the combination are going to be the same, just to add this term here. So this term is very important, as you saw. So we are summarizing in this slide this term and the dependence of this term on the parameters. So you can see that it's linear with the increment of temperature, that in our case will be negative because it will be the difference between the autoclave, the curing temperature, sorry, to the service temperature. And we have also some functions that are analytical and depend on the material and laminate properties that you can see here. So we designed some experimental campaign for evaluating if this, let's say, strategy is accurate or not for the prediction. We did some classical specimen, plain specimen that are classical for this kind of composite. With the next strategies, we fix the ratio of the outer to the inner ply thickness in order to fix this parameter. In order to fix this parameter here, and we fix, of course, the material. So all the parameters here are fixed. So what we expect is that the residual elastic strength, this term that adding to the mechanical strength, taking into account the residual thermal stresses, is linear with the temperature. And this is what we want to evaluate experimentally. So we fabricated 5 specimens per laminate thickness, and the others are the classical ideas. Concerning the experimental setup, we use a monotonic tensile testing machine, the classical one, mechanical one, and with a strain rate that is very classical also in composite. But the interesting thing, the new thing, let's say, is that we are using a climate chamber in order to modify the residual thermal stresses. As the residual thermal stresses come from the decrease of temperature from the curing temperature to the test temperature, if we can't modify the curing temperature because it's given by the fabricant and also is a chemical optimization. If we modify the temperature at which the test is down, we will be modifying actually this decrease of temperature. So we expect to modify the residual thermal stresses. So we tested at this 3 temperature our specimen, of course, we control the temperature and we detect the transverse cracking with acoustic emission. That is the classical method used in this kind of experiments. So these are the preliminary experimental result that we obtained. So we are plotting here for the 3 thickness. The first is the thinnest, the medium, and the thickest laminates. In horizontal, we have the temperature of the experiment, and in the vertical axis, we have the strain level at which we detected the first crack onset. We are actually plotting 2 levels of strain, one for the very first crack onset, that is the first acoustic event that we associated to a transverse crack, but also the strain level at which we have some consecutive cracks that are very close in time, because the first one can be a defect that is propagating or so on. So we are plotting the 2. And in green, you can see these lines correspond to the tendency predicted by the theory that we are presenting here. As you remember, this is linear with the temperature, and that's why here you have a straight line. We are plotting a lot because if we focus on one of the 4 theories that we are trying to improve, let's say, we will have 1 for each theory. But we want to do this comparison independent of the theory of the Borjak, incremental couple, etc., that we are taking, because it's gonna introduce in our comparison all the fracture and strain property of the lamina, etc. So in this case, all the results are only dependent on the elastic property and thermal properties that, as you know, are easier, much easier to obtain, and they are more reliability. So as you can observe, the results are not very good. Let's say that for the thinnest laminate, that it's sometimes you have other kind of failure like delamination, free edge delamination, etc., etc. The tendency qualitatively is okay, but the quantitatively we have a lot of scatter. We have a high level of scatter, as you can see. For the medium thickness, we have better results, and for the thickest laminates, we have results that are, let's say, more or less correct. But anyway, they are preliminary experiments, definitely. So to conclude, we have developed a general formulation to introduce the effect of the residual thermal stresses, and this formulation is very easy to apply to all the models that are the most popular in composite. It's just to add a term to the strength that we have mechanically. We have compared that with the experiment, with some preliminary experimental campaign. At a qualitative level, the increasing tendency is predicted well, but at quantitative level, the predictions are not good, and we need more experiment to verify this is correct, and or if we need to take into account other kind of phenomena in our strategy. So to finish, we are planning to do, of course, a new experimental campaign with more specimen and more laminate thickness. We need to improve the knowledge about the failure or the event that we are detecting with the acoustic emission. Actually, we are collaborating with some colleagues already on this topic. And finally, we need to measure the residual thermal stresses directly, because now we are actually seeing or measuring the consequence of these residual thermal stresses that are the critical strength at which the crack appear. But we could actually measure the residual thermal stresses directly in our laminate before testing them. So in order to have an intermediate result to compare with our theory. And that's all. Thank you for your attention.